Yeah.
Yep, thank you. Well, it looks like it's time to get started. Kind of a small class today. Thanks for making it. I think I mentioned last time that this is usually the hardest class to attend right before the break. We might get some others in, but looks like for the moment it's just you. I'll try not to put you on the spot the entire time, though. I'll probably talk to the Zoom camera, the understanding that people are probably going to see this a little bit later on. But since it's just you today, thanks for making it in. You pretty much have the floor. Or we have another one. I was just telling Aliana that she was pretty much had the floor today, but any questions to start us out to either one of you?
Questions about what?
That's a great question. Really anything at all.
Oh, and
Yeah, questions about the course, quiz, homework, or whatsoever. Just questions to start us out.
Keep missing. That.
You could always make up anything that went past due for full credit. So no, it won't affect you too badly. Gotcha. That's pretty normal for, I think, how the semester goes. Other classes sometimes butt in with their projects and such. And for me personally, Thanksgiving break is kind of a catch-up week on Monday, Tuesday, Wednesday, either anyways. So yeah, you can always make it up for full credit. Absolutely. Other questions at the moment?
with anybody on Zoom?
No, it's just us today. So they'll be watching on YouTube later is what I'm gonna assume. So we'll try to still kind of make a good video from them. Appreciate you folks actually making it in person today. My last class, if you're curious, is a fully online class, and for a big part of it, it was just me doing a YouTube video. It's a really weird way to teach. But Thursday, right before the break, it's a weird day anyway. So I would have canceled this class potentially, except I already had 2 sick days, so it felt like a bad call. So we'll get through it today. For the announcements, quiz number 10 is due today, but it looks like it's already been handed in by both of you, so we're all set there. This is just a quick question right here about quiz 10 standard error. Right now we're in section 15.3, about ready to look into the mechanics of a hypothesis test. We'll probably get through one full one on today's class, but there's no new quiz today. So if you're wondering where it is, my thought was we're on a big break, and having a quiz due across a Thanksgiving break is not the nicest thing to do. But also another reason no quiz this week is because I feel like doing a few problems here, or at least 2 problems, is going to be a good deal for the quiz. Our next quiz 11 is going to be based on that section 15.3. So it felt like a little premature to ask a quiz on this one anyways, when we're just getting started on it. But that's a quick run up of the announcements. The whole purpose of section 15.1 was setting up hypotheses. And those are the very first steps in section 15.3. So now we're going to look into the rest of the mechanics with hypothesis testing. We looked at this page kind of briefly the last like 6 to 7 minutes of class. The very first page in section 15.3 is just a roundup of formulas we've seen before, just to kind of get them all in one spot. The statistic p hat and the parameter p are defined. The central limit theorem is given along with its conditions. And then finally, when we come down here, this is kind of in the wrong spot. The new material is really right over there. It's just a restatement of the z-score formula. The z-score counts the number of standard deviations in your data value. Y is away from your mean, y bar. But the central limit theorem is now telling us we have a different kind, well, I should scroll that far. We have a different kind of data value. The thing that's playing the role of the data value is now p hat this time. And by the central limit theorem, the mean of the statistic p hat is the true proportion p. But that's going to be p naught because what's highlighted in purple is the very first assumption we make in hypothesis testing is that the null hypothesis is actually true. So that means the mean, back up here in the central limit theorem, the mean is p, but it turns into P naught through the null hypothesis. Then you divide by the standard deviation. Notice it doesn't say SE for standard error any longer. That's a pretty big warning on this already. Standard error of P hat is square root P hat. Let me kind of fix my penmanship on that first. The standard error of P hat is the square root of P hat times 1 minus P hat divided by the sample size n, and that's not what this is at all. It has the same exact format, but you're using the value from the null hypothesis directly. So this is not the same.
So that would have been like in those previous problems, like the 65%.
What do you mean, say 15.1? Yeah, the P naughts would have been those values, the hypothesized value. Let me double check just to be completely sure. 15.1, I think you're right. Yeah, now that I'm remembering, we highlighted the parameter in yellow, but we wrote in black the P naught 0.45. It goes right down in here. And yeah, that's absolutely right. That's the value that's going to be plugged in both in that location for the test statistic. So that's the hypothesized value. Try and move that up. Goes right there in the null hypothesis, just like down below here. And it gets plugged into the standard error as well. So everything highlighted in blue with that color coding just goes into all those 4 different spots. It makes spotting that value like one of the more important things, right? Knowing what the hypothesized value is, gives you your null alternative, allows you to measure the test statistic and your standard deviation at the same time. Well, this concept is also the same. Z-score tells you how many standard deviations the data value is away from the mean. This below is a Z-score, and this tells us how many standard deviations the statistic P hat is away from P naught and the null hypothesis H naught. That's a lot of symbols. Essentially, it's telling us how far away is our data in terms of the statistic P hat from the assumption you made in the null hypothesis that the parameter P is in fact the hypothesized value, P sub 0. So if those standard deviations are a lot, we're almost definitely rejecting the null hypothesis. But if it's borderline, we need a hard and fast rule to decide when are we rejecting and when are we going to fail to reject. So that's the tie-in with the Z-score. That's the major reason we looked into the Z-score and did some problems to get a feel for what it's doing. It's because it comes back into hypothesis testing, both in this section and the next. So measures number of standard deviations, P hat is away from P naught, assuming H naught is true. And looking at this once again, the only thing we haven't talked about really that much yet is what in the world is the significance value, another Greek letter alpha. So you see this, it's like an infinity sign, but you don't complete it all the way. You just go kind of like halfway, a little over half. This is read as alpha. So the significance level alpha sounds important. Plays this role down below here. You test the null against an alternative, any 3, but we put in the default test. Will be tested at the significance level alpha. And we find out what is the probability of getting a Z-score as extreme as we got from our data, or even more extreme. That probability is going to be the p-value. So we'll see on how to compute the p-value in the next chunk of the notes. But this is how we decide what to do. If the p-level or the p-value is less than the significance level alpha, that doesn't actually highlight too well. Let's just go like that. If we have a small p-value, then we're going to reject the null hypothesis in favor of the alternative. If you have a rather large p-value, we'll fail to reject the null hypothesis and say we didn't have any statistical evidence, significant evidence, the alternative is true. So that's the role alpha is playing. But what we need to know is, what are typical values of alpha? there's usually three great choices, and they go like this. Alpha equals 0.10 is one choice. Another middle road choice is 0.05. This is a pretty common choice to make, but if we want a high level of evidence before we are determined to reject the null hypothesis, we want to gather a lot of evidence before we accept this, we go for alpha equals 0.01. So this is requiring high level of evidence. This is a little bit lower, and we would never go above that as at alpha level. Going higher than that would be very, very strange. But this might kind of sound familiar to you already. These get paired off with something that's similar. Hypothesis testing and confidence intervals kind of go together. And these are just significant levels on the left that are typical. Once you decide on a significance level, and you decide to also do a confidence interval analysis, here's what you would have on the right. Confidence levels. If you do a significance test at a significance level alpha 0.10, that means you're probably thinking of a confidence interval, C equals 90%. A 90% confidence interval is like a 0.10 alpha level for a hypothesis test, and we'd always keep these the same. If you're doing that hypothesis test, your confidence interval analysis can't be a 99% confidence interval. It needs to stay as a 90% confidence interval, or else conclusions could get kind of crossed and mixed match if we did that. Likewise, at a 0.05 significance level, confidence is a 95% confidence interval. At a 0.01, this is where we need a lot of evidence to reject the null hypothesis. But that's where we want to be really highly confident in our confidence interval of capturing the true parameter. That's the 99% confidence interval. So notice these would always, if they're both written as a percentage, add up to 100%. So this would be a 10% added to 90, 5% added to 95, a 1% added to 99. And they're all completely paired in that sense. So that kind of tells us what alpha is all about. And there's a lot of stuff going on with hypothesis testing. You can probably kind of see why we did confidence intervals first. This is a lot of mechanics. Any questions or thoughts at the moment with what we've written down? Okay, so just to think about this, I'm going to put down some notes that I'll erase so that this doesn't get too busy if you ever come back here. Let's suppose, just for a random example, the hypothesized value was 0.68, just the number that popped into my head. So you're going to test the null hypothesis. The true parameter is 0.68, 68% rate of successes in the population. There'd be a 0.68 here. But let's say you collected your random sample of size n, and p hat came out as maybe 0.32. Way, way off of the hypothesized value. That'd be so severe if our sample size is decent, like say 30 or 100, that this is so going to be assuredly a lot of standard deviations. The p-value is going to be the probability of getting a test statistic z as significant as what this would be, or more significant, under the assumption the null hypothesis is true. That'd be a really, really small p-value. And even if alpha was at 0.01, our p-value would probably be even smaller. And we would say, well, the probability of getting a statistic that small, assuming the null hypothesis is true, is so vanishingly small, less than alpha that we set, that it seems like the null hypothesis is just unreasonable, and we reject it and conclude the alternative was the truth about the population. So that's the kind of logic about what the p-value is, how it ties in with the significance level alpha. I think actually calculating the p-values helps to make more sense, but does that kind of clarify it a little bit? If it's still kind of clear as mud, that makes sense. This is a lot of stuff at the moment. Kind of crazy so far? Gotcha. We'll come back to this table when we go through the full mechanics. So this is something we'll revisit. But let's put down just something in words, just as a way to kind of, actually, let's leave these on for the moment and then put it in words to connect the thought. The p-value is the probability or chance, let's just say probability, of computing a z test statistic referring to this one right here when we say z test statistic as extreme sorry, my control Z's going in random directions, as extreme as this study, or more extreme assuming H naught, P equals that hypothesized value P naught is true. So in our extreme case, if the data is at 0.32, but we hypothesized it came from a population at proportion 0.68, that is really extreme. And that would be a small chance for that to happen by random, giving us a small p-value altogether. But if we measured, say, 0.67, and they're really, really close, we're probably not going to say that the probability of getting that is very high. That seems like random error could get you that value above or below just by random chance. That's when the p-value is large in this case, and that's when we fail to reject the null hypothesis. Our data is pretty compatible with what the null hypothesis was saying. So again, it's a lot of mechanics so far. The next thing we're going to take a look into is how do you actually calculate the p-values? It's kind of cool because you just go back to chapter 5. You go to your calculator in chapter 5, use normal CDF, and it's just area under the normal distribution. So let's look into the next phase. Well, down below here is the next phase. I forgot I have an example in the middle. I think that's probably a good idea. Here's the next phase where it shows how to actually calculate all of those p-values. But before we go into this table here, this is a kind of a warm-up example getting to that spot. So I forgot I had this example 1 here. Probably good. It gives us a little bit of break of what we were looking at above. So we looked at these data before from the last section. This is the one where we stated the hypotheses, we defined the parameter, and just so that we don't have to do it twice, it's been redone down here as well in this block of text. But to remind ourselves, this is what was going on in the problem. We're looking at the National Center for Education Statistics, which monitored many aspects of elementary, secondary education nationwide. The 1996 numbers said 34% of students had not been absent from school even once during the previous month. But that was the hypothesized value in the problem. And these notes were highlighting hypothesized value using blue. So let's keep that color coding. That's the new thing that we're interested in. So here's the hypothesized value, the 1996 data. So 34% of students had been absent from school even once. We're told in a year 2000 survey, responses from 8,302 students, so there's our sample size, show that this figure slipped to a p-hat value. This was the statistic we discussed, to 0.33, coming from the 33%. Officials would be concerned if this attendance has declined. So we're asking the question, do we have significant statistical evidence of a decline in student attendance? Because we said decline, we have a less than, it's a left tail test in this case. But the hypothesized value goes in both of those spots. Our significance level alpha is a 0.05. So when we calculate a p-value here, if it's below that 0.05, we're going to reject that null hypothesis here and say we have evidence that this alternative is true. And the parameter P is just defined probably pretty close to what we did before, maybe slightly different language. Proportion of all students that had not been absent from school even once during the previous month. And we said in year 2000, not the 1994. That's what just the baseline we're comparing it to. So here's one of our new things. We just highlighted this in yellow. That's the significance level alpha. Part A is now asking the question, tying together the concepts we were looking at the last set of notes. How many standard deviations is the sample proportion of successes away from the hypothesized value? Well, when it said sample proportion of successes, that's p hat. And so we can write out this. When it asks how many standard deviations, that's really just a z-score. So z is going to be equal to a p hat minus the p naught value. And the whole thing is going to be divided by the standard deviation of p hat. So out of nowhere, we're going back to the central limit theorem. Let me open another section of notes so we're not scrolling up and down constantly. We're going back to section 13.2 and using the central limit theorem from way back in the day. It wasn't that long ago, but sometimes when you get farther along the notes, it really feels that way. So where's the central limit theorem? Here it is. It says the mean of the sampling distribution is P. That's P, but we assume the null hypothesis is true as our very, very first step, just like in a court of law. So you actually have a value for P. It's 0.34 that goes there. So we're taking a data value, the statistic from the sample, minus the mean, that's what we do with the z-score, divide by the standard deviation, but we have a standard deviation formula. I'm going to put in Q1 minus P. In place of P, we are actually putting in P naught, this value right here. So just from the central limit theorem, we can say standard deviation of P hat. We can now actually calculate this thing. It's square root of P naught, 1 minus P naught, divide by the sample size n. And there's that one warning once again. This feels so similar to writing out standard error, SE of P hat. But if we did a standard error, that's a confidence interval problem, and we have to put P hat there. So we're using P naught instead and rewriting this now as square root 0.34, then 1 minus 0.34, divide by sample size n, which in this problem is 8302. Jam that all into the calculator, and we'll have the standard deviation of P hat. Gonna need a little bit more space, it turns out. Does that make sense to folks so far, using these two formulas from above? Okay, let's put it in the calculator next. Feels just like calculating standard error. You hit square root, go 0.34, 1 minus the 0.34, divided by 8302. Our value, let's see, we're rounding to 4 decimal places. So I'll go to slightly more on this one so we can round at the final step, 0.005199. I would have rounded it to 5 decimal places, but rounding with carry is kind of annoying. So I went for the extra 6 decimal place. It's a good idea to be a little bit more accurate here and only round to the 4th place on your final step. So this is just a z-score formula. It counts number of standard deviations. So that's in the way it's answering this part, how many standard deviations. Let's actually convey that thought there. How many standard deviations is just that whole thing. So now when we plug in the formula, we'll have put in our value for p hat. I just have it in black because I'm running out of colors I can load up. 0.33 minus the hypothesized value, the baseline number, 34%, but as a decimal, 0.34. Really, it's the same value put in your null hypothesis and alternative. It's off by just 1%, but that's not the full story because look how small the standard deviation is. It's a very, very large sample study, so standard deviation is really, really minuscule. 0.005199. So let's compute this. It is 0.33 minus 0.34 divide by 0.005199. And in terms of standard deviations, let's round this to 4 decimal places. It's negative 1.9234. And you know, that's kind of a lot of standard deviations. Once you're getting close to 2 standard deviations, it's a significant amount. 3 standard deviations is a very large amount. 4 or 5 standard deviations is simply gargantuan for hypothesis testing. But 2 standard deviations nearly, even if it's positive or negative, the direction isn't the major thing. It's about 2 standard deviations. That's sort of borderline as well. Significance level alpha is kind of the middle road for amount of evidence we want. But the fact that it's negative isn't too surprising if we're doing a left tail test. If we had a right tail test, it could have been positive or negative, but for a right tail test, we often expect probably positive here. So just to convey the thought, we now have that p hat is negative 1.9234 standard deviations away from the value in H naught. We have to decide how unusual is that. Because it's borderline, we need a guidance, and that's our benchmark. If our probability that we're going to compute drops below 0.05, we'll say that's the level at which we have significance, that this is, in fact, pretty unusual. Our sample data is too far away from the null hypothesis for the null to be reasonable. So that's going to be the next step, actually computing the p-value next. This is a good amount of the logic of hypothesis testing so far. Does it make sense on what we did on paper here for the z-score? Okay, well, if we can get a z-score, calculating the p-value is really nice. It's a full-on review of section 5.4 when we were doing the normal distribution. First thing when we calculated normal probabilities is we just drew a rough sketch of the normal curve. That's always a good guidance. And the distribution we're using is strictly the standard deviation every single time, n0, 1. 0 is the value for mu, 1 is the value for sigma. So right here in the middle is 0 on this distribution. Next thing we put down is the z-score we just calculated, negative 1.9234. It would be somewhere, say, about here. So here's z, negative 1.9234. And now the next thing we do is we had to decide which direction we shaded, right? Whenever we did these computations. But here's the dead giveaway. The problem is asking, we want to know if there was a decline in student attendance. That right there was the research question. It's telling us that's a left tail test. And if it's a left tail test, what we do is we go from here and we shade going off to the left specifically. So that's how all these ideas kind of cascade down. And this area right here is going to tell us the chance of getting a statistic as extreme as 0.33 when we assume the truth of the population is that it's 34%, 0.34. So it's just right there. That's the p-value, the area itself. So the p-value is this area. So to get it, we use normal CDF. And using normal CDF in our calculator, we have to put in a lower bound. But if we're shading to the left, this is assuming shading without ever stopping. So the lower bound is negative 10 power 99. I think equality actually makes more sense there. The upper bound is where we stop shading right up to this point. So that's inputs 2, the upper. And inputs 3 and 4 are mu and sigma, but it's always 0, 1. So now back to the calculator, hit second bars. So normal CDF problem, since we're going for areas. Hit enter on this. And this calculator already has the right value in. If you had something typed in differently, you might have wrote it in like this, negative 10 power 99. The other version was just the calculator's way of saying the same exact thing. Upper is negative 1.9234. And the 0 and 1 is already set up here. So to get your p-value, it's got to look just exactly like that. Hit enter a bunch of times, compute it out. And here's what the p-value comes out as. The p-value for this particular test is 0.0272. Well, we've got a p-value, but really the major purpose of example 1 is to really see what's going on with the logic of hypothesis testing, which is very tricky. So let's think about this p-value a little bit more.
Is z-score with a positive value, would it be on the other side?
Yeah, absolutely. Your z would be way over here, and now your p-value would be something like, say, 97% and some change. It'd be a very large p-value in that
But
case.
the z-score is always going to be the upper.
Depends on that right there. So this less than right here is going to tell us the direction to shade.
Oh, perfect.
That's a good thing to put in the notes. Thanks for asking about that. I want to put here, we shaded to the left because it was a left tail test. Let me rewrite this as shade to the left, since in the alternative hypothesis up here, we put in a less than for the left tailed test. Yeah, I think that's the smarter comment to make on this. Then the area is just that shaded area right there, giving you the p-value. That's what made the last section 15.1 so hugely pivotal, right? If you can get that inequality just right, you'll know the direction that you're going to shade, left or right, and then it becomes the full-on review problem of chapter 5 material. Other questions or thoughts so far? Okay, so what did the p-value measure? In words, we can say it this way. This is a 2.72% chance of getting a value of p hat. That's the statistic we computed. P hat was 0.33. P hat equals 0.33 or less, assuming the true population proportion P is 0.34. Assuming the null hypothesis is true, take a random sample of size 8,302, there is only a 2.72% chance of getting a 0.33 for the sample proportion of successes when you make that assumption. And that percent chance is low. It's less than the 5% chance. So this can't happen often. And that was our bench line for finding enough evidence against the null hypothesis. That means we're going to reject it in this problem. But so far, that's what the mechanics are. The z-score is the number of standard deviations your statistic is away from the statement in the null. The p-value is the probability of getting that statistic as extreme as 0.33 or even more extreme. And it's just a shaded area right here, matching the direction of the test. The next thing that's tricky is this table right here. Let's copy this back in. This tells us the decision we make. But remember the goal. The goal is we're the researcher. We're trying to show the alternative is true. And what we want to show that that's true is that this can't happen, that value and that value in the statistic very often, that the probability is low. We want to find small probabilities, in other words. Small probabilities give us evidence for the alternative. So part D is now giving a conclusion based on what we found, just trying to find a place to scroll to, based on what the p-value is. Once you compute the p-value, you want to look up the significance level alpha again, 0.05. So let's write that in. We have alpha equals 0.05. I think we highlighted that in yellow. Since the p-value in this problem equals 0.0272, and it's less than the 0.05, our benchmark for finding significant statistical evidence, we are in this case, the good case, the one in green, green for good or go, I guess. We will reject the null hypothesis. We'll say essentially, but we have to write it in with the context. That's always the hardest part to remember. That the study found significant statistical evidence that the alternative hypothesis is actually true. So that's what we're going to make as a conclusion. So in order to make that conclusion, we go all the way back to the top again. We need to know what the alternative hypothesis was. We need to know exactly what we said the parameter was. So this is the line we'd be looking in. Let me move this down just a little bit. But first, does it make sense on why we're making this decision, rejecting the null?
It's less than that.
Exactly.
Value.
That's the whole reason. As soon as our p-value is less, we reject, as in this case. Let's say right here, just to organize our thoughts, this means right arrow for the conclusion, reject H naught. We're going to say that event is too rare of event for us to accept it any longer. And this is tricky because rare things do happen, but based on one study, this was our benchmark for evidence. If we really want to know if this is a real effect in the population, we have to repeat the study. And if we reject again, we start to get overwhelming evidence against the null hypothesis. But here's the next thing we have to look into.
Did we explain that already?
Which part?
Which one, what is the null hypothesis and the alternative?
Actually, we kind of did. This was just copied down from when we were in section 15.1. In 15.1, the problem we're looking into is the very last problem right here. And I felt like it'd be too redundant for us to rewrite that again. So when I wrote out these notes, I just typed out what we said from before. So yeah, it's kind of like a carryover problem where we did this once, but not on this set of notes. Other questions so far? Okay, so here's what your mind might be thinking. Reject H naught means it's gone, completely gone from consideration. That's our conclusion. But this is super similar to when we made a practical interpretation of a confidence interval. We're going to come back over here and just read it out what it says directly based on what we said the parameter was. The only difference is I don't have a lower bound or upper bound. There's no confidence interval anymore. So we can say for the practical interpretation, the following. We have significant statistical evidence And I'll put here in parentheses because unfortunately not everyone wants to say this every time, and it's kind of strange. I'll say in parentheses, just as an optional thing you may or may not say, at the 5% significance level, I think it's weird that our books don't always say that we should write that down every time. It's kind of like not writing down the confidence level when you do a confidence interval. Whether we rejected the null hypothesis or not, depended on what you put here. If we put in a 0.01, we would not have rejected the null hypothesis. So I'd like to write this in as just an extra explanation, but it is optional, so that's why it's in parentheses. We have significant statistical evidence at the 5% significance level that come down here and just write out the statement. P less than 0.34 is not something we can put down. The practical interpretation has to be something that makes sense to everybody when they go to read out your results. So we'll say what P directly was from our prior statement. That, you could say proportion or percent, I'll go with proportion, that the proportion of all students that had not been absent from school even once in the prior month in year 2000. It's a long statement, but all we did was we wrote out what P was. Then we'll say is less than, because that's our alternative hypothesis, P less than. So I'll just say here is less than. Then we just say the hypothesized value, 0.34. So that's essentially how this goes. Very similar to confidence intervals, except all we're reading out this time is what the alternative hypothesis statement was by redefining P, putting it back in context. Well, we did it, folks. That's the first hypothesis test conclusion we've done the whole semester. I mean, we're at the end of the semester and we just discussed it. But any last questions at all on how to get there? Any one of those moving parts? Okay, so again, hypothesis testing has lots going on with it. There's a lots to put together, a lot of moving parts, a lot of just new terms like test statistic. That was the Z value. P value is a new concept, even though it's a familiar process, the way it comes together is new and it's a new terminology. And significance level alpha is a new terminology as well. Not to mention the null and alternative. There's just lots going on. There's lots of white noise basically that we have to filter through. So that's why in these notes, we're going to practice 3 more full problems from top to finish for all tests, left tail, right tail, and two tail tests together. But before we move on to the next portion of all of this, there's a what if problem we should take a look into. We had a pretty generous level of evidence that we're going for. It's like a 95% confidence interval. It wasn't the highest benchmark for evidence ever. A higher benchmark for evidence would have been 0.01. So we might wonder, if we were writing down a conclusion for 0.01, what would that look like? This is somehow a lot trickier when you get to this stage. Because when alpha is 0.01, let's go through the same logic. Alpha is 0.01. We'll say since the p-value, it wouldn't change if you change the significance level alpha. The p-value equals 0.0272. Well, this time, 0.0272 is big. It's in this case. It's strictly bigger than, but I'll write bigger than or equals to remember that even if it was 0.01, it's still considered big in that case. It's bigger than or equal to 0.01, which is equal to alpha. And this means the decision is different. We're not going to reject H naught. This implies, as opposed to that direction, we will fail to reject H naught. So we'll say fail to reject H naught. And that's a weird statement to write. When you say fail to reject, we're going to say exactly what that means by writing down in this what if situation, what if it was 0.01? What is the conclusion as a practical interpretation this time in context? Here's why it's so tricky. If we go back to 15.1, we can never, no matter how convincing the data looks, make a conclusion that the null hypothesis is true. Failing to reject the null hypothesis is not accepting it. And it's the same thing we were harping on the first day of chapter 15 in a court of law. Geez, that just keeps going. In a court of law, you might have seen this happening in the news, that someone didn't meet the benchmark to say a person is guilty beyond a reasonable doubt. And then we say, well, all the jury says not guilty, but what they didn't mean is we proved that they are not guilty. The null hypothesis, the defendant is not guilty, is never proven in a court of law. We just never met the required benchmark to prove that he is in fact guilty or she is in fact guilty beyond a reasonable doubt. So people get off scot-free, even though everyone feels like they could be guilty or not. The null hypothesis is never resolved even in a court of law whatsoever legally. And same issue here. Failing to reject the null hypothesis just means still we don't accept the null. It's still out of the question. We just say we failed to provide evidence for the statement HA, whatever it was. So it's kind of a gloomy statement that you make, but it's the honest statistical statement that we're never proving a parameter equals a particular value. That's impossible. At best, I can give you a confidence interval estimate, but nothing more. So here we'll say, this is kind of tedious or redundant, so bear with me. The practical interpretation this time is, I'll save just a little bit of writing. We failed to find significant statistical evidence and let's say at what level, because the significance level alpha is what's controlling all this. Much like when you give a confidence interval estimate, we say at what level of confidence you have. So I'll say here at the 1% significance level, just as a reminder, that's a tough benchmark of evidence to beat. That. Then we come back down here and just rewrite out the statement. The proportion of all students that had not been absent. Should have wrote out a faster parameter for this, but let's get our way through it. Even once last month in 2000, feels like I'm abbreviating just a touch more. So far I wrote out the P part and I'll say is less than. I then put in 0.34. So that's the entire interpretation going in that direction. I'm going to put a border here just to convey the problem is over right there. But I won't leave the notes down below, just as a reminder of how we got to this conclusion this time. Failing to reject the null hypothesis means this is what your statement looks like. The easiest mistake to make in the world is to accidentally say, we have found significant statistical evidence that the proportion of all students that have not been absent at least once in the last month in 2000 is 34%. We can never say is 34%. all we can say is we didn't find any evidence that it's less than 34%. So those are the major things we've been harping on quite a bit whenever we were talking about we can never make a conclusion that asserts the null hypothesis is true. And this is what it looks like on paper for just a different significance level alpha. Well, any last questions or thoughts, folks, thinking about this process so far? Okay, well, that's our first top to bottom hypothesis test. One thing I should mention when it comes to statistical studies, whenever you write out what you're about to do in a statistical test, whenever you're about to do a study, you write down your null and alternative hypotheses really carefully, and then you never change them. You'll never change from a less than to a not equals, for example, or less than to a greater than. That'd be even more concerning. And another thing you can never change once you go and collect the data, no matter what the data looks like, is you can never change alpha. In fact, a lot of studies say if they're funded by the government, you have to tell the government before you get your governmental funding what your null is, your alternative, your parameter, your population, and what your alpha level is. You submit all of that first, then they give you money and you collect your sample. And if you did your statistics and decided, well, it was 0.01, but I wanted to reject, so I changed it to 0.05, the USA government is going to go after you for that, and they're probably going to want some of that money back. You can never change alpha when it's put down on paper. No matter what the data looks like, we have to stick to our guns. It's all set in stone before we even grab the sample. So this is a what if that never actually happens in practice. It was just for the sake of us writing down the two different conclusions. The next thing we want to do in these notes is to say, how do you get the p-value in essentially any situation whatsoever? We did the left-tailed test, but if it was a right-tailed test, we would have shaded to the right. And if it's two-tailed test, we use both tails. So we want to specify that. That's the purpose of this next block right down below here. Large sample test for a proportion. We finally have conditions, the test statistic, the standard deviation all in one spot and a null hypothesis. So we use this test as long as we have two conditions. We have a simple random sample from a population of interest, and it's selected in a way that should result in a representative sample. This is the one that requires a lot of statisticians and a lot of discipline-specific experts to justify if it really was representative. Our hope is that it was just a bona fide simple random sample because it takes a lot of the guesswork out, whether the sample's biased or not. We also need a large sample size. Well, let's take a look at this under the view of section 13.3. We had conditions here too. The things always look a little bit different when you go from conditions in a confidence interval to conditions in a hypothesis test. So the best way to tie these together is let's look at them side by side. So here's the confidence interval. Let's go down to these conditions. Large sample confidence interval for a population proportion P is dual to the hypothesis test for that same proportion. Sample has to be random. Part ones are really the same kind of statements rather. The sample is large as statement number 2, but large has a totally different meaning this time. Large down below here meant the number of successes in the sample and the number of failures in the sample had to be at least 10. So you could just count them up, or you could use these formulas right here. This is not the same at all. What we're seeing above is the number of successes that we expect to see in the sample. I don't know why these are so hard to move sometimes. Hang on. So n times p naught, recall p naught is the hypothesized value, the thing we've been color coding in green in these whole notes. This is not the number of successes in the sample. In fact, you can run a hypothesis test with 0 successes in your sample whatsoever. It's totally appropriate. It's only valid, however, if expected number of successes exceeds 10. So this is the number of successes we expect to see when H naught, P equals the hypothesized value P naught once again, is true. And likewise, this is the expected number of failures as well. So it's a totally different computation, and that's something that's really easy to miss when you go to calculate this out. So condition checking is a little bit trickier on these, but then going down below, the p-value is honestly not too bad. We've done one already, the left tail test. Every one of these p-values depends on what is the hypothesized value in your null hypothesis. So if you can spot that, and you know exactly what the parameter p is, you've done all the heavy lifting essentially. All these are just formulas you crank out in your calculator. The last thing, the p-value, is totally determined by the type of test you're running. Let's make this the last concept of the day, since I don't think we have enough time to run through a complete problem like the one down below. We'll fill out this table, take some questions, and probably end class a little bit earlier today. Any questions at the moment with just the conditions or the roundup of formulas again? Okay, let's start with something familiar. The p-value is calculated as follows. We've done a left tail test, and here's what it looks like. In words, it's the area under the z-curve coming from the z-test statistic, so whatever that value z is, to the left, area under the z-curve to the left, calculated value of the test statistic. That's kind of a confusing way to say it. Let me change this to uppercase Z. Sorry, I didn't notice that before releasing these notes. When they mean Z-curve, uppercase Z helps us remind us that it's the normal distribution. Okay, that was only in these two spots. So just as a reminder for that correction, Z is distributed as N01. So if we write it out here, here's the normal curve, Z, which is distributed as N01. We put 0 in the middle, just like we did on our other problem. Put down wherever Z is. This test statistic for a left tail test, we usually assume it's way out here on the negative end, but you know, it could be anywhere whatsoever. It could be to the right of 0, could be to the left of 0. Let me just write a slightly better looking normal curve. If you put your Z right over here, that's something that could happen. This would be a case where you're going to probably, almost assuredly, fail to reject the null hypothesis because this is your p-value and it's rather kind of large. So the p-value is going to be this. You would put in for input 1, lower equals negative 10 power 99. Inputs 2, upper, is whatever your z-test statistic came out as. You get that area below, and in each case for a p-value, you use normal CDF each and every time. So this is the test we just ran. We had something significant when it was at 0.05. This would be something that's not significant, probably like a 0.30 for a p-value. Now, if we're doing the right tail test, it all changes once again, but not by a whole lot. The new situation is just that we're going to shade in a different direction. So here's N01 once again. This is something where we'd probably fail to reject the null hypothesis. If we put Z somewhere over here, now it's pretty borderline. It's going to depend on what the significance level alpha was. But this area right here is your p-value this time. We're shading to the right only because of the right direction. Shade to the right. And in the left tail test, we shaded to the left only because of the less than direction, or the fact that it said left is a dead giveaway. So this was shade to the left. So we shade to the right here. Calculator work is almost identical, except this time, input 1, lower, is equal to your test statistic Z, whatever it is. Let me put it in on the same color as before, as black. Input 2, the upper value, is going to be 10 power 99, because now we're shading to the right end without ever stopping. So those are the two tests so far. Any questions at the moment? Okay, now here's the next thing that's kind of unfortunate about this. The tricky one is the two-tailed test. But the two-tailed test is the default test, so it's in some sense the most important one to describe. And there's two kind of scenarios that comes up with a two-tailed test. Your test statistic is either positive or negative, and that matters on how we're going to calculate this. So we'll write down two graphs for each situation. In all of these cases, we're dealing with N01. Doesn't hurt to write that out each time just to make a specific reminder. Okay, so first situation, Z comes out positive in your test statistic. So maybe it's somewhere over here. There's your Z. In the second situation, Z comes out negative. So maybe it's over here this time for our Z. So whether it's positive or negative is just the position it is across the zero value. And notice for the two-tailed test, whenever you're doing a two-tailed test, the major feature about this is you're going to take 2 times the area, either to the right of Z or 2 times the area to the left of Z. So that's the major idea. So here, if it's positive, you'll double this area. On the second panel, if it's negative, double this area. And doesn't quite convey why it's a two-tailed test, but here's the logic behind this. I want to take this off the notes after I put it down. This is more just an explanation. But once you put a Z here, there's another Z-score that goes here and another set of area. This is why it's called a two-tailed test. There's 2 areas that you're really filling out. This one on the left and this one on the right. But because the normal distribution is completely symmetric, instead of putting down the areas twice, you can put it down once and just double that area right there. Or put it down once on this end and just double this area. So you'll have to make sure you put in for, in this case, the lower equals Z, upper is 10 power 99. In the case on the left, lower equals negative 10 power 99. 2 upper equals positive 10 power 99. And here is the major supercritical thing. Be sure to double the area after using normal CDF. So whatever area you get, we have to be sure to double it. That's easy to forget. That's what the ×2 is all about in the notes above. Instead of shading the two tails, I just shaded what it's going to look like in your calculator because I feel like that's going to make it actually easier to use when we go to take a look at these notes once again. Oh, that's a good question. It would look more like this. You'll get an area, and then the calculator will go just ×2. So for a really quick demonstration, let's say we go to second vars, normal CDF. Let's pretend our Z is in this situation. It's a negative 1.9234, same Z value as before. That means lower is negative 10 power 99, upper is 10 power 99. The Z, or hang on, I wrote this weird. Let me fix my notes first before I answer that. On the second panel here, the lower was right, but the upper value was Z, the test statistic. Sorry for that error right there. So I'm trying to double it on this panel right here just for the demonstration. Z is the old test statistic we ran before. Then you hit enter a bunch of times and you get a number out, but doubling it means just go times 2 in your calculator to get that value out. So doubling it just means go times 2 in that case. Well, other questions about that so far? Okay, well, this is a lot of stuff we did so far today, folks. Thanks for making it in today. Today was kind of the heaviest day of the week. I mean, aside from the fact we did an exam, that's probably worse. But today was a no easy measure. When we come back Monday after the holiday, we'll be a little bit more well rested. We'll revisit these notes right here on this page on how to run the hypothesis tests. And then we'll do 3 tests from scratch, starting on example 2 down below. Well, any last questions or comments at all, folks, before we call it a night? Okay. Well, thanks for coming, folks. Have a great Thanksgiving. We'll be back to it next week. If you have any questions over the holiday, don't hesitate to email. I'll be available checking my email pretty much on the mornings. Thanks, you too.